Let's look at the linear algebra we'll need for this course. Starting with the linear transformation L, when it acts on a linear combination, it breaks up the sum and it pulls out the constants. Breaking up the sum, that's called additivity. Pulling out the constants, homogeneity. So L is additive and homogeneous. Geometrically, we have an input space, we have an output space, and we have a transformation taking one to the other. What we are taking are vectors. We make a basis in the input space so that every other vector is a linear combination of these. Linear combinations of basis vectors is parallel translation geometrically. Scaling. And adding. Each basis vector gets fed through the transformation and outputs another vector. Taking linear combination of these vectors makes another grid by parallel translation. That L is linear means that the linear combination of the input is the same as the linear combination of the output. So the output vector is the same linear combination as the input vector. It points to a point with the same grid location. Here we're using the duality between points and vectors. It's not really a dual, it's really an isomorphism. A bicontinuous function taking points to vectors that respects addition and scaling. There's two different notations, angle brackets or column. We will use column vectors. Angle brackets will be used for inner products later. So our mapping takes the vectors 3, 2 and outputs the vector 3 L of the first basis element, 2 L of the second basis element. But those are vectors in the blue space. Using the basis for the blue space, this is the vector 3, 1 and the vector 1, 2. There's a shorthand notation, the matrix vector notation for this linear combination, which defines the matrix for L with respect to this basis choice. The output vector points to the point 11, 7. So I can think of L taking the point 3, 2 and generating the point 11, 7 through the isomorphism. Before we do that, just a notation refresher. The notation for the matrix is exactly the same as for the transformation. The only difference is parentheses are not. No parentheses, it's the matrix. Parentheses, it's the transformation. When you write the matrix, you're choosing a basis. When you write the transformation, it's a basis-free description. Let's take a closer look at the point vector isomorphism. So phi is taking components of points to basis vectors. I can scale vectors. And I can add vectors. I can take linear combinations of vectors. Traveling through phi inverse. I have now defined linear combinations of points through this isomorphism. Putting this all together, these are the kind of pictures we're going to be drawing. I have some point of interest, and I put a vector space centered at that point of interest. I can access other points in that vector space. And then feed the whole thing through a linear transformation. It can be an output point of interest, not through the linear transformation. The linear transformation just takes the vectors to the vectors. So it takes the grid to the grid, the space to the space. And the corresponding point in the space gets mapped over. But the output point also has the standard basis. Using the standard basis at my output point, it has a coordinate. But if I think of it instead as looking at an offset, from the origin, that offset is really what we're looking at. It's a 3-2 offset in the black basis. It's a 11-7 offset in the standard basis.